Alright, so in this video I'm gonna be explaining another important paper with the title Locality Aware Graph Rewiring in Graph Neural Network. We sometimes use graph rewiring to avoid over-squashing in graph neural networks. So this iClear paper in 2024 is very important. So graph rewiring techniques have been proposed as a means of improving information flow by altering the graph connectivity. In this work, we identify three desidera for graph rewiring: reduce over-squashing, respect the locality of the graph, and preserve the sparsity of the graph. Spatial rewiring techniques partly preserve the graph distance information, for example, its locality, by only adding edges within a certain radius or by relying on positional information. However, these methods often result in a dense computational graph that increases memory complexity and can cause issues such as oversmoothing. You see here the difference between spectral, which is on the left, spatial, which is on the middle, and the laser on the right. The technique of this method, this paper, these rewirings in green with respect to the blue node of the reference. So it remains both local and sparse by optimizing over edges to be added. Now in this message passing paradigm, like previous video that I said, here they are using effective resistance. And you know that the commute time in graph theory, the commute time between any two nodes is proportional to their effective resistance. That's why effective resistance is a very intrinsic thing for understanding graph topology. And I've talked a lot about over-squashing long-range interactions. The main principle behind graph rewiring is to decouple the input graph from the computational one. Rewiring consists of applying an operation to the graph, thereby producing a new graph on the same vertices but with altered connectivity. Of course, if we don't say it explicitly, it damages the graph topology, so we should be very careful about it. Now you see properties of different types of rewiring. The laser has all of these three things: reduces over-squashing, preserves locality, preserves sparsity. So main contribution is this novel paradigm for graph rewiring that leverages a key principle. Instead of considering a single rewired graph, we use a sequence of rewired graph, such that for smaller L, the new edges added are more local and sample based on optimizing a connectivity measure. So we discuss a general graph rewiring paradigm that can enhance any message passing neural network. So consider trajectory of rewiring operations. We go from graph G0, we do rewiring, it becomes graph G1. Another rewiring, it becomes graph G2 until the L3 rewiring that becomes graph G sub L. So we think of G sub L as the input graph evolved along a dynamical process for L iterations. Just like diffusion in computer vision, ideas of normalizing flow diffusion, spatial diffusion that starts with the noise gradually after many functions applied to that, it becomes an image. The same idea is here. Several times you apply same rewiring several times until a graph becomes a totally different graph. The first property we demand of the rewiring sequence is that for all nodes, we have this mu of u and v for the next iteration greater than mu. So it's monotonic. I forgot to say this connectivity measure mu, that can be any topological quantity that captures how easily different pairs of nodes can communicate in a graph, while the measure nu is any quantity that penalizes interactions among nodes. So we constrain each rewiring by requiring the measure nu to take values in a certain range. We expand this idea of this paper in 2022 by noticing that the general sequential rewiring paradigm can be instantiated as a family of multi-relational graph neural networks. And so we rewrite this equation like this. So we see how our choice of sequential rewiring can be interpreted as an extension of relational rewiring. We choose nu to be shortest walk distance. And for connectivity measure mu, we can use this a to the k, the number of walks from v to u of length at most k. Because the length is at most k, so a to the k is enough for the connectivity information between two nodes u and v. So take the adjacency if you to the power of k and look at the uv entry u and v. Look at this. This is the connectivity between u and v. So now we describe our method. Given a node v and a snapshot g, then we consider the set of nodes at distance exactly L plus 1 from v, and we introduce a global parameter rho. And add edges among v and the fraction rho of nodes with the lowest connectivity score. If this fraction is smaller than 1, then we round it to 1. So we end up adding only a percentage of edges that a normal multi-hop GNNs would. Because GNN has problems, it creates problem over squashing. And to avoid that, people created rewiring. But rewiring changes graph topology. So what's the point of this? In applying rewiring, we should be clearly separate our summations in order to. Otherwise, if you just add edges, nodes, it totally damages the topology, which is the global structure of the graph. But this paper is very interesting. It has good theoretical foundations, which adds an edge between nodes with the highest effective resistance. This effective resistance, like previous video, is very important for graph topology. And they did experiments because over-squashing happens in large graphs, for example. That's why peptides functions, peptide structs. These two data sets you see in almost all papers that are about over-squashing. So this is the algorithm. Given the graph, the locality matrix D and the connectivity matrix M, a locality value R, and density rho, we want to find the rewired edges for particular locality R.